Okay, so we're recording. Off we go. So, here's where we were last time. We were talking about triple integrals. We have a definition here. Remember, the big idea of a triple integrals is pretty much just a rip-off of the idea of double integrals, except instead of having stuff distributed over an area or that we view by breaking it up according to chopping up some area. Instead, here we're addressing problems where stuff is either distributed over a solid or is being broken up into pieces according to how we would break up a solid. So it's a fundamentally different kind of thing in that it's three-dimensional, but it's structurally, strategically pretty much the same idea as a double integral. Okay, so we wrote down this definition. And saw a quick observation about how, for example, mass of a three-dimensional solid can be argued as the whole of the sum of the parts, and mass is mass per unit volume times volume. Again, as is mass per unit volume's job, right? That's what it's supposed to do. Okay, so this sort of strategy here allows you to take a question and turn it into a triple integral. Then finally, I gave you all a sort of a strategic warning. Watch out for this mistake. Don't make the mistake of thinking that you can understand triple integrals from the point of view of graphs. You can't. That would be a four-dimensional picture. You can't do that. Right? I mean, it's just not realistic. Much better, and I won't get back onto my soapbox on this, but much better if only for the purpose of setting yourself up for being able to understand triple integrals, even ignoring other advantages, right? I think much better to think about single variable integrals in terms of the classic mass of a rod example, and double integrals in terms of how you would compute mass if it's distributed over an area or thought of as distributed over an area. And then what's a triple integral? And no sweat, same thing. Now the mass is distributed over a solid instead of an area or an interval. So dimensionally very natural. Okay, and that's about where we left off. Okay, so picking up from there, and let's see here. Let me, wrong button. Let me do it like that, and of course this is in the way. Let me do that again. Okay, picking up from there. There are several arguments that we made about double integrals that, as much as I advise against the point of view for these purposes, were very convenient at the time, and tragically I can't make those graph point of view arguments for triple integrals because the dimensions don't work out. Again, here's kind of our roadmap for how we did double integrals, right? And remember, a prominent player was the question of volume under the graph. That's three-dimensional for a double integral, which means that if I try to make such arguments for triple integrals, there would be some sort of four-dimensional notion of what would you call that? Four volume, maybe something like that, right? And it's not that you can't do that, but the point that I'm making here is it is not intuitively satisfying. It's not a good idea to try to base our conclusions on arguments that would go to trying to understand some four-dimensional thing. That's not a good plan. Right, so we do have to make different arguments. It remains, of course, that if you can't understand a concept, then you can't obviously connect it to physical ideas, right? It's sort of an automatic. And I'm going to say it also remains that things like trying to understand mass immediately with an iterated integral, again, mismatches. You're going to be talking about mass per unit volume times length. And again, mass per unit volume was not expecting to be multiplied by length. It's not immediately clear what that means. It's a real problem. Okay. So you can see this coming. We are going to, just like we did with double integrals, end up with this three-step process for how we're going to solve problems with triple integrals. We've already seen arguably two of these three steps. We've seen how you can take applications and turn them into triple integrals. The whole is the sum of the parts, and if you have the associated density, you write it down. Right? mass of a solid. We just saw that example a minute ago. And I'm going to say we've kind of seen this. We haven't technically seen a triple iterated integral, but it's the same idea as a double iterated integral. And we're going to spend a bunch of time today talking about how to create these iterated integrals. What we have not talked about yet, and I'm going to kind of wave my hands at it, is how do I know that I can always turn a triple integral into a iterated integral? And how did I do this back with double integrals? Well, I made this clever argument involving volumes, and of course I can't do that now. So I'm not going to be able to give you an argument here. So that's, I'm going to say, unsatisfying, and there is a way to make this argument, by the way. It just doesn't go by way of any geometric ideas. The way you make this argument is a purely algebraic argument. And two things. First of all, it's very rigorous. It's very it has some sticky wickets, some formality issues that are worrisome and problematic and have to be dealt with. And that's not really what the focus of this course is about. And also, it is, I'm going to say, low return or area of investigation as far as Math219 is concerned, because you'd kind of expect this to work. It worked for double integrals. Wouldn't you expect it would work for triple integrals? And so I think it's just a bad investment of time to pursue that point. So I'm going to ask you to take it on faith that triple integrals can be turned into iterated integrals, and it's exactly the same process, exactly what you would expect. Okay, so again, please always give me the triple integral. Please don't just go straight from an application question to an iterated integral. That makes it look like you're making an argument that doesn't hold water, right? The triple integral is the thing that makes the argument hold water. So please make sure to give it to me. In this course, and of course what you do outside of Math219 is your business, and I get it, but anyway, in this course, I need to see it. Okay, so here's an example. Let's compute the amount of mass in this rectangular box, which, by the way, you can probably guess the notation. This tells you the interval that is the x shadow, if you will, of your box. And then here is your y shadow, and here is your z shadow. Those are the intervals on the corresponding axes that define this box. And mass is distributed over that box according to this density, this mass per unit volume. And the question is, how do I compute the total mass? So, okay, no big deal. How do we compute mass? Well, we just got through arguing whole is the sum of the parts and density and all that mass can be computed with a triple integral. Okay, so that's our phase one of the problem. Turning the application into a triple integral. There it is. Application, triple integral. Okay. Next step. We've got to figure out how to turn the triple integral into an iterated integral. And again, I'm not going to show you process on this, but it's exactly what you would hope. Triple integral is exactly the triple integral you would expect and hope. You have options as to what order you put your differentials. You have 6 options, right? It's not just how do you order 2 things, it's how do you order 3 things, and there's all sorts of different ways to kind of shuffle things around there, right? So a lot of options there. And you just have to make sure that your bounds of your integrals inside of your iterated integral match up with the rectangular box in question. So for example, notice that my y bounds here are the y bounds of the box, right? And notice my x bounds here are my x range for the box. And just to be thorough, the z bounds are the z range for the box. So exactly what you would expect. Further, exactly what you would expect, the integrand is the same, just like with double integrals. Okay, how are we doing on that part? Everybody buy it? Okay. All right, so we've done that part. Now the last part is plug and chug. I'm going to be quick with this because it's just like with double integrals. Oh my gosh, it's exactly the same thing, just one more step. It's 3 instead of 2, right? So you're going to notice, and again, I'm just going to kind of wave my hands at this, but notice we go inside out. We start on the inside. You have to. I can't even talk about doing my x integral until I know what my x integrand is, which I can't do till I do the z integral. So you have to go inside out. Don't forget that while you are doing the inside integral, your outside variables are treated as constants. And so notice that the x and the y here, constants. And the action, what's really happened when I did that dz inside integral, for the second term that is, the 2z turned into the z squared, right? That's where the anti-differentiation, the activity, that's where something actually happened. The constants stick around for the ride, and variables further to the outside are constants. Okay. All right, and then lastly, super quick, I think it's a healthy exercise to, when you put your z bounds here to be evaluated, I think it's a healthy exercise to put this little reminder here that those are z values. So easy to accidentally, because of a lack of reminder, plug in z values for x and y or something like that. And again, it'd be inadvertent. Obviously, you wouldn't do it on purpose, but this can help reduce that inadvertent mistake. Okay, the rest of this is an easy read. Make sure you can do it. Follow through here. Make sure you're good with all that. Obviously, the integration's not particularly tricky, but you want to think through how in each different stage here, it's a different variable that's behaving as the variable, and etc. Okay. Alrighty, so now on with the fun stuff. What do you do when your domain's not a rectangle? What do you do if you want to add up mass, for example, over some sort of lump like this instead of a rectangular box? And how are you going to deal with the lumpiness, the non-rectangularness of that domain? And good news, it's just like double integrals. And recall, when we were doing double integrals, we considered a picture like this. We used the volume question, despite the fact that I've been trash talking that a little bit here, because it's it's kind of a dead end in terms of physical intuition. But it sure is convenient for certain purposes like this one. And we argued that the iterated integral, because of the shape of the domain, right? The shape of the domain gives rise to functions that are the inner bounds. Right? And we further argued that you don't even really need to see the three-dimensional picture to make this argument. We noticed that all that really mattered was the shape of the domain itself. And so we simplified and streamlined our picture to just look at the domain. Right? And we argued specifically that we started off, now as I have it drawn here, let's see here, you'll notice that I am doing what I'm going to call my y slicing first, right? So I had a bunch of slices perpendicular to the y-axis. Looking at the range of values for y, we decided what the starting value of y was, what the ending value of y was. Right? And then we fix a value of y, and then move on to the next variable. Now we're going to start thinking about as I slice up in the x direction, and there is a starting value of x, and then as I slice my slice, there is eventually an ending value of x, which depends on the previously arbitrarily chosen y. Right? That's the process. While I'm here, I'll emphasize, just to be clear, and as hopefully obvious, right? But the whole point of these being functions is that it depends on the shape, right? So you, very importantly, when you're looking for these x bounds, you're looking not on the entire shape. You're not looking for what is the lowest value of x anywhere on your solid, which might be, a little lower, or a little upper bound might be a little higher, right? That's not what we're looking for. The x bounds ignore the whole solid. The x bounds are only interested in the range of values of x on the y slice. That's what gives us a shape as opposed to just a big rectangle. I mean, does that make sense to everybody? All right, so let's keep all that in mind. And going back to our triple integral scenario, I claim it's the same process. Pretty much the same process. Now, I can't draw the four-dimensional picture, obviously, right? But we can follow the look only at the domain analogous process. And we're going to slice in one direction, think about the bounds from the first and last slices, fix a slice, and then go back and then slice in the next direction, and then identify the bounds in that next direction, and then etc. Right, so we're going to cycle through the same three-step kind of process, just now in three directions instead of two. So here's what that looks like in action. Again, we've got this big lumpy solid here. Now I'm going to start by thinking about x slices. By the way, no particular reason. This was an arbitrary choice. I put dx on the outside. Doesn't matter. It's a little bit easier to draw the picture this way. Just to have something to do, I needed to make a choice there. So slicing perpendicular to the x-axis. Here's what a slice looks like. Perpendicular to the x-axis. And I can see where the first one is. The very first one is going to be that, whatever is the farthest in the page, the farthest back point on my solid, and that's going to have an x-coordinate. That is my lower bound. Right? And then likewise, there is a last slice, which is going to be this point right there, kind of furthest out of the page. That has an x-coordinate. And that's our upper bound. Right? So nothing to it. Let me, I should zoom out so I can fit this on. Here we go. And you can see now we've got our x bounds. Cool. Alrighty. So now with that in mind, x bounds having been determined, we fix a slice. We fix a value of x. We focus now all of our attention on that slice. After all, our y and z bounds are going to depend on x. They only depend on x if I determine them based on looking only at a given value of x. So we're going to treat x now as a constant. It's determined, and on that slice, and only on that slice, we proceed to the next question, which is, what's the range of values of y? Well, okay, the y slices kind of look like this. A little hard to draw in there. The colors get a little muddled. Sorry about that. But those are what y slices look like. And again, very importantly, not y slices of the solid. Y slices of my x slice that I've already made. Okay. And now it's easier to clean up if I do that. So looking at this this kind of a slice, notice that there is going to be a first one, which will have a y coordinate, and there's going to be a last one, which will also have a y coordinate. That gives me my y bounds. Notice, as you would expect, those y bounds are functions of x. As they should be. I mean, you look at the shape, you can imagine as that x coordinate moves, as you're looking at different green slices perpendicular to the x-axis, yeah, the cross-section that you're looking at is going to be totally different. The y coordinates then will be totally different. So the bounds depend on x. Everybody all with me? Everybody happy? Okay. And now we fix not only x but also y. We focus now on a point, a slice, a y slice of my x slice. Notice that y slice of my x slice now is just a line segment. And you got to use your geometric intuition here. The x slices are kind of like this, and then if I slice the slice kind of like that, it's like I'm intersecting two planes, two vertical planes, and they intersect in that little line segment. On that, we now look for the range of values of z. On that slice, there is a lowest value. That's your lower bound. There is a highest point with a highest z value. That is your upper bound. And notice those are, as expected, functions of x and y. Which, again, as they should be. Again, you look at the picture. So that's our process. I'm going to suggest we kind of dive right in to see this in action. Oh, real quick, before we dive in, I do want to make some qualitative observations. Notice, and again, as justified by the picture, for the purposes of the dy integral, x is a constant. Right? We fixed a value of x there. So I get to treat x as a constant for that entire dy integral. And likewise, and arguably even before that, you might say, looking at the dz integral. For dz, the dz integral happens kind of in some sense on just that little line segment, and so both x and y I get to treat as constants as I'm going through and doing the antiderivatives, etc. Variables further to the outside are constant. Okay. And again, watch out for the language. You got to be careful with the first, second, third. I like outside and inside for the outside and inside integrals. The one that's in the middle, you can call it middle, I suppose. Also, conveniently, you can call it second, because it really is second, whichever direction you're going, right? So, sometimes life is good. Okay. Again, notice we construct the integral by our slicing process, starting on the outside, going to the inside. We evaluate the other way. We evaluate from inside out. So, confusing. Okay. All right, we've already talked about these other points. Okay, so diving into an actual geometric example, let's look at this example right here. Oh, and I should mention, this is a good time to pause real quick. Notice how the pictures are heavily three-dimensional. Notice how much we're relying on the pictures. You're going to notice that even more as we go through more and more examples. It is really important, not just for your ability to kind of think things through, but also for you to be able to communicate your ideas, for you to be able to communicate without ambiguity that you had a valid argument in your head when you were writing down your work, right? You need to be able to draw at least a reasonably believable picture. It doesn't have to be beautiful. It doesn't have to be frameable, right? Doesn't have to make a statement about society, right? The bar is low, right? But it does have to accurately represent what it is that we're talking about three-dimensionally, and that's pretty hard to do, especially if you haven't practiced it. So I think it's unavoidably critical in this course that everybody become reasonably competent at drawing three-dimensional figures, if only for this circumstance right here. So now, if you're good at it already, cool. If you're not, which I think is most students in the class, right? Practice is important, but also there are things to know. There are little tips and tricks for how to make things in ways that you not necessarily even conscious of, make things just kind of look better, look more three-dimensional. And I have documented everything that I know about three-dimensional drawing, and I'm going to claim some competence in this, right? That's pretty decent, right? It's not, again, not frameable, right? But you get the idea of what I'm describing here geometrically, right? And I did that with just lines. Right? So, anyway, everything that I know about three-dimensional drawing is in a pair of videos that I have on my miscellaneous topics playlist on the YouTube channel. They're called Drawing 1 and Drawing 2. I guess I wasn't feeling very creative when I titled them, right? I think you'll find it really useful. I really do, right? So I strongly encourage everybody to take a look at it, right? Click through if you're bored while I'm talking about something. Yeah, okay, got it. Then just fast forward a minute or whatever, right? But please do give it a look. I think you'll find it helpful. And then, by the way, of course, practice makes perfect. This is not just a matter of knowledge. This is a matter of chops. You got to do it with your hand, right? On the test, we're going to be using paper. No iPads and cool, straight line. They're the little option where you can make it where it magically just makes a perfectly straight line, stuff like that, right? No such benefits on the exam. So practice will also be important. Okay. All right. Okay. So anyway, here we go. We're interested in a triple integral on this solid tetrahedron. Again, not worrying about phase one. What's the application here? Whatever. Maybe I'm computing a mass. Who cares? Whatever. I just want to focus on how to turn the triple integral into an iterated integral. That's it. Right? Okay. All right. So no particular reason I'm going to order my differentials like this. We'll talk later about how to make good decisions on how to order your differentials. So that being the case, I'm doing my dx on the outside, so slices perpendicular to the x-axis. Those slices look like that. Three-dimensional visualizing, right? Not hard to persuade yourself that the first slice is there. The last slice is here. And now look, sometimes the fish jump in the boat. I mean, it's pretty immediately clear that my lower bound then is going to be 0. After all, that entire lower bound slice is in the plane with equation x equals 0, right? So that's a freebie. And again, sometimes you get lucky and life is good. Okay, but let's talk now instead about what about this upper bound? Where does x2 come from? And this is where you have to, again, follow the method. You gotta don't try to just kind of make educated guesses based on the algebra that came to you and just kind of write down, take some excerpt from the given algebra and copy that into the bounds. I've heard horror stories of students from their high school multivariable calculus classes saying, that's what my high school teacher told me to do. Oh my gosh, right? That's absolutely not an argument. Right. Okay, so here's the process. The process is, step 1, identify the relevant point. There it is. That's the point that identifies the upper bound we're looking for. That point is on what geometric objects that I can identify. And thankfully, from the picture, I can identify 3 geometric objects that point is on. For one thing, it's on that face, which has that equation. Now, next observation, and again, thank you, picture, it is clearly on that face, which has that equation. And again, oh my gosh, can you imagine trying to do this without a picture? Thankfully, from the picture, I can see that it's on this angled face. Sort of the front, sort of kind of sloping backward kind of shape. And that has this equation, which we were given. How we doing? Okay. All right, now, again, I got all that from the picture. Really good that I have the picture. Okay, now next step in the process is, we've already identified the relevant geometric objects, we've written down their equations, and now we just have to recall that we're looking for an x bound, and so in this little trio of equations, I need to solve for x. So, again, easy to lose track of what you're doing, right, but you can solve for x, and again, this is an easy one. Solving for x, we get this. That then is our upper bound. Everybody see the process. Now again, what we're interested in here is not whether you agree that that's what the upper bound should be. What I'm interested in is, does everybody see the multi-step process? We identify that last slice by a point. We understand what geometric objects it's on from the picture. We write down the corresponding equations. We solve for the relevant variable. Okay, cool. Sweet. Off we go to the next direction. So having fixed a value of x, now we're going to look in the y direction. So as I go and do slices in the y direction, those slices will look like this. All right, and let's think about first and last. The first one is here, very conveniently already obviously in the plane where y equals 0, so I know y is going to be 0. So again, sometimes it's easy, you get lucky, gotta love it. And then, let's see here, for the upper bound, though, the upper bound is going to come from that point. And again, here's where I have to start thinking carefully. What do I know about that point? Okay, so first thing to observe, I know what x is. X has been fixed. You don't have to write down x equals x. That's a little security blanket for me. That's my little visual reminder to myself that we know what x is. It's been designated. It's whatever it is. X is x. Again, you don't have to write that down. I just find that satisfying. So we know what x is, but I also know the point I'm interested in, the point that determines the y2 that I care about. Check it out. It's in that plane. Thank you, picture. Only because of the picture can I see that the point, that a critical little point that identifies my upper bound for y. The picture is what tells me it's in that plane, which has that equation. So again, as I promised, notice how much we're using the picture. Okay. And then lastly, let's see here. And again, thank you, picture. I see it's in that plane that we were given, which has that equation. Right, so again, I've got some algebra that defines that point. I am looking for a y bound. So in this set of equations, I solve for y. And notice you get a function of x, as you should. Yeah? Okay. And so that is your y upper bound. Okay. All right, and then same process again with x and y both set. In other words, looking over a single point, you might say in the xy plane, and now looking in the z direction. Of course, we're going to go just kind of from there to there. And again, sometimes the fish jump in the boat. Obviously, the lower bound is 0. The point defining the lower bound is in the plane z equals 0. It's right there looking at us. Take the wins when you get them. The upper bound, that point there. How are we going to figure out the upper bound for z? Well, that upper bound for z, we already know what x is. We already know what y is. those are settled. And the critical other piece of information that I can see here is that the point that I'm looking for is in that plane, again, that we were given. Again, thank you, picture. And so there's our algebra, and trying to solve for the z coordinate. We solve for z in this equation, and we get that, which is our upper bound for z. So now notice it's the same. I cycled through basically the same process 3 different times, right? Very important to see that it's just 3 repetitions of the same basic idea, but each sort of iteration, you might say, of this same process is in a different direction and with different knowns and variables playing different roles, etc. Okay, all right. Okay, all right. By the way, on this particular example, just looking at the shape of this tetrahedron here, I think it's a pretty easy pitch that it doesn't really matter which order you slice. Here, if we had done dy dx dz, it wouldn't be that different. So for whatever it's worth, I encourage you to give that a shot. Think about, pick your whatever, it doesn't matter, some random different ordering of these differentials, and just think it through and write down the bounds and compare with a friend, perhaps, right? If you both get the same answer, that's a good sign. If you get different answers, you've got a topic of conversation to discuss, learning experience for everybody. Okay. All right. All right. Just like with double integrals, try not to slice through corners. Bad things happen when you slice through corners, just like with double integrals, right? So that's a good thing to try to avoid. If one of the variables kind of naturally looks like a function of the others, you're going to want to arrange that is the variable that you have to solve for, because it's clearly desirably to be solved for, not the other way around. So you try to put that one on the inside. Right? And there's one other little bit of advice that I write down just because I wanted to have all the bits of advice together, but I'm not really quite ready to tell you what I mean yet by a projection or by a good projection. So we're going to come back to that. The next example is going to illustrate what all that means. So here's the next example, and let's see. Oh, I didn't zoom out enough. There we go. So we've got this weird shape here. Notice how it comes from the geometric description in the statement of the question. First octant bounded by a paraboloid that you see there, and sort of capped at the top with z equals 1. Okay. All right, tell you what I notice. Now there's shape in front of us, and I can think about all different kind of ways to possibly slice it, but I notice that z is more naturally a function of x and y than any other such arrangement, and that makes me want to put dz on the inside. Seem like a reasonable choice? All right, so with dz on the inside, that means, unavoidably, that I'm going to have dx and dy on the outside. Now, which one is all the way to the outside and which one is in the middle? I'm going to claim that actually doesn't really matter too much in this case. Every example is different, of course. After we go through this example, you can satisfy your curiosity about the possible merits of switching by just switching them and going through the process again and seeing what happens. And I think what you'll find is that it doesn't really matter much. Okay. All right. So we're going to be doing our dx and dy on the outside, and I claim this is related to what I'm going to call a good projection. There's 2 aspects of a good projection. One is I'm going to argue that our solid here, our actual solid, our actual solid here has a lot in common with its projection, its shadow down here. in the xy plane. Why xy plane? Because we have x and y on the outside. You're going to see how that plays in just a moment. Okay, so good projection in the sense that that's a reasonably desirable shape. It's a quarter disc. All else being equal, I don't really like square roots, but I don't think I'm going to be able to get out of here without square roots, and not so bad. Okay, so why this shadow is useful comes with the slicing process. Let's think now about how would I slice up my solid, and how would I slice up the shadow in the y direction. Again, outside in, right? We've got dy on the outside. So, okay, well, a y slice of the solid looks like that. And it's a little bit hard to draw. But you can imagine, I'll tell you what, I'm going to clean. Oh, that's exactly what I didn't want to erase. I'm going to clean up the inside. What I have in purple there is a y slice of my solid. And correspondingly, this is a y slice of my shadow, and notice they're right on top of each other. After all, if you think about it, when you take a solid and when you push it down into the xy plane, projecting perfectly vertically into the xy plane, it doesn't change the x and y coordinates. Projecting leaves x and y coordinates the same. You're just losing the z. So of course they have the same x and y, and therefore, more to the point, y coordinates. So very nicely, I don't need to look at this picture to see the lower bound for y. I can see the lower bound for y. Here, let me. I can see the lower bound for y. That is hard to draw there. I can see it by just looking at the lower bound for y on the projection. I can see the upper bound for y there just by looking at the upper bound for y on the projection. I don't need to look at the solid. Just look at the projection. That's pretty handy, right? So that makes it a lot easier to determine those bounds. And then likewise, moving on now to, let's just get rid of all of this. Looking at a y slice, we'll fix a value of y. There again is this hard to draw y slice of the solid. There's this much easier to draw y slice of my projection. What's the range of values of x? Well, x starts, you might say, these points looking at the x slice of my y slice of my solid, or I could just see it right down here in the projection. A lot easier to see. And again, likewise, as you go along, there's your last x slice, or looking at the projection, just much easier. So it's a really cool observation, very powerful, very convenient observation, that whatever variables you have on the outside, whichever pair of variables you put on the outside, you can look at the shadow in that coordinate plane and use only that to determine your outside, your two most outside bounds. And I think this is just awesome. I'm 2/3 of the way done with finding my bounds, and I don't even have to look at the solid. Everybody see this? This is a cool trick. I don't know why they don't talk about this in the book. This is totally awesome. I'm a big proponent. Okay, now you do have to look at the picture for the inside bounds. After all, with x and y fixed, in other words, looking above a single point, the z bounds are going to come from looking at the range of values of z. You can see z is going to kind of go from sort of the bottom to the top there. And this gets to the second point of what do I mean by a good projection. Notice, to find my lower bound, I'm going to have to look at this lower bound point. I'm going to have to understand z is a function of x and y. At that point, or in general, on my lower surface. So another requirement I'm going to throw in here, what I'm going to need is for that surface to be what I'm going to call consistently the same surface. I don't want to have some deal where, well, the lower bound's going to come from this one surface on, over here, but it's going to be this other surface and they kind of intersect. No, you don't want any of that. That's going to make things ugly. But very conveniently here, check it out. That every X and Y, every point in the projection, looking straight up, the lowest value of Z is going to come from a point on that green surface, and it's always the same green surface. So it's always easy to solve for Z, and you get a single expression, and that's your lower bound for Z. Everybody cool? Likewise with the upper, right? So my upper bound for Z, well, it's always, there it is. It's always going to be a point like that, which is always going to be on that surface. Consistently, always the same, by the way, very nice surface, right? With an equation that I know in which it's, again, convenient to solve for Z. That gives me my upper bound. So now we can go back up here, and now you can see what I mean by a good projection. You want to have a shadow that's easy to slice up. What I call a desirable shadow. And you want to have good top and bottom surfaces that are consistently the same and not hard to deal with. So whenever you see this, whenever you see a good shadow and consistent and convenient top and bottom surfaces, you've got yourself a good projection. Put those two variables on the outside, and you get to find most of your bounds by just looking at the shadow alone, just like we just did. Okay. All right. So here's another example. Looking at I should go ahead and zoom out here. Looking at this, suppose I want to do an integral on the unit ball for whatever reason. Well, you can slice your slices, etc., and draw the pictures. And by the way, have fun with this one. It's a lot harder to draw than you would think. Give it a try. I think it's a nice little exercise to try to draw a sphere and a slice of the sphere and a slice of the slice, and it gets a little challenging. Right? Not that you can't do it, but it's challenging. Right? And if you do that, you will get the right bounds, and this is what they end up being. But look how much easier it is if you think about the projection. Now, arbitrarily, no particular reason, in this case anyway, I'm going to do my differentials in this order, and so Z and X are on the outside. All right, well, what's the shadow of this ball in the XZ plane? And it's going to be a disk, unit disk no less, which I feel compelled to shade all the way in. There we go. And how do we slice up a unit disk? Well, y'all have probably done that before. And my X and Z bounds on a unit disk are just like this. You don't need a three-dimensional picture for that. Just look at a unit disk in the XZ plane. Just draw yourself a little axis system and play the game, and boom, bounds. We're 2/3 of the way there. Everybody happy? Then there's the question of, okay, what's the lower bound surface? What's the upper bound surface? Okay, well, for given values of X and Y, like if I were to pick of X and Z, if I were to pick an X and Z sort of there, then it's such a hard picture to draw. I don't think that's very good, though. Let's see here. Let me try to do it about like that. So Y will range from what you might call the back surface to what you might call let's say the left surface to the right surface. In this case, it's not really up and down. It's sort of left and right, just because of how I ordered the differentials. And notice that my lower bound point is always going to be on the sphere, where Y is negative. Solve for Y in the equation of the unit sphere. Easy to do. Notice that my upper bound for y will always be at a point that's on kind of the right half of the sphere. Again, solve for y. Same equation. Very, very similar solution. The only difference being that we pick, because in this picture it's clear y is positive, the positive value for y. Everybody see how this put together? I think this is a lot easier than drawing slices of slices myself. In many cases, I don't want to overgeneralize, right? Not always, but surprisingly often. It's a great point of view. Okay, yes?
Yeah, before we go on to this, but what do you do when it's not so easy to know what the maxes are?
Then you have a hard problem. Yeah, and so I should confess that, I'm not going to show you methods that will allow you easily to solve any problem at all, right? There are genuinely hard ones. I'm going to, again, put some tools in your toolbox, right? That's really all I can do is just kind of show you a bunch of different representative collection of examples that illustrate how to use the best tools that I can give you reasonably in this course, and that's just all we can do. Yeah. Right. Okay. All right. Okay, moving along. I love this example. It's a hard one, but it illustrates some excellent points in here. So first, let's try to figure out what on earth is this thing right here, the region bounded by these 5 planes. Now that, if I were to give you 5 random planes, just try to imagine how sort of 5 random planes, how do they intersect, and what is there a unique region that's bounded by the 5 planes? How do I know there's not more than one region bounded? That's a really hard problem in general. But there's something really special about this example, and again, just one thing to remember, I'm not ever going to give you an unfair question. Right? There will always be a foot in the door to turn what could have been an impossible problem into something tractable. And the big point here is that you're going to notice 3 of these 5 equations don't have any y's in them. And flashing back to like day 1 of this course, if there's no y in the equation, it's parallel to the y-axis. So these are actually really easy to draw. You just have to think about, I know they're going to be parallel to the y-axis, so I really only need to understand what they look like in the xz plane, and that combined with the fact that they're parallel to the y-axis is game over. So for example, let's look at z equals x. And that's going to be confusing. How do I draw that plane? Well, first just draw z equals x in the xz plane. That's easy. That's just a 45-degree line. And then reminding ourselves that it's parallel to the y-axis, I can just kind of drag parallel to the y-axis. And you could repeat for these other 3 planes. Right? Whoopsie. And in particular, these 3 in the xz plane kind of look like that. And now drag that parallel to the y-axis, and you're going to get something kind of vaguely, you're going to get a prism. So that allows us to have understood 3 of our 5 planes in an easy way. And now we just have to think, okay, well, what happens with the last 2? And since I already have so much to work with, it's going to be a lot easier to interpret these last 2. So y equals 0, yeah, sure. Y equals 0 is going to intersect my prism like so. The last one's a little annoying. How do I deal with that? Oh, gosh. Okay, well... Oh, man. This has X, Y, and Z intercepts that are clearly all 3, and so I can kind of do like that, and now I appeal to your geometric intuition. How does, if I were to take this kind of angled plane back here and kind of cut, imagine cutting at this, it's an angle like this, how would that cut through my existing prism? And kind of cuts through in a way kind of like this. And if you have trouble with the perspective on this, and how do I know, for example, where that point is, and how do I know where that point is? If you just need a little help on a couple of the details, in other words, you can just do the algebra. Just solve for where those points are. No big deal. Is that cool? Okay. All right. So that gives us this picture, which otherwise, in general, for if I were to give you a random 5 planes, that'd be really, 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 really hard. But because we have this foot in the door, not so bad. Okay, so that's a nice trick, nice tool for your toolbox. So now, how are we going to slice this up? What order are we going to do our differentials? It really matters for this example. That's why I say this is kind of a hard example. Things get weird if you slice in a bad order. So, for example, what if I slice with dy on the outside? So let's suppose that I do like this, and now I've got to look at slices perpendicular to the y-axis. Well, for this value of y there, you could imagine a y slice would look something like that. But as y increases, you're eventually going to hit that corner, aren't you? And then, life gets weird. Let's see, it's going to be something like, it's going to kind of, something maybe more like that. Because you slice through a corner. That's to be avoided. Oh my gosh, and then look, you also slice through this corner, after which your slices are going to look even still more different. Something like that. The pictures are hard to draw. Clearly bad choice. So I think it's a nice little exercise in geometric challenge to think through all 6 of your options. Give it a shot. And I think what you're going to find is that in 5 of these 6 options, you're going to slice through corners. There's only 1 of your 6 options that doesn't slice through corners. And that's this ordering right here. So that's is pretty geometrically challenging. It's a tough game to play. I mean, how would you figure this out without just trial and error of going through all 6 options, right? It seems like that could be bad. So this is another example where the projection point of view pays off pretty big time, right? Now here's that same picture, but let's just notice that the projection into the, whoopsie, I wanted the highlighter here. The projection into the XZ plane is a triangle. That's easy to deal with. That's a nice projection. My lower bound surface, as the other variable y, what's going to be the inside variable y goes from lowest to highest. The lower bound is always going to be on that same plane, consistently, always the same plane. Which, by the way, I see from the picture, right? Where does the upper bound come from? Well, the upper bound point is always going to be on this plane, always the same plane, consistently. So this is a really good direction to do your projection and make a projection argument. Now, before we proceed with that, let's just notice how bad it is in other directions. What if I tried to project down here to the xy plane? If I use that as my projection, well, my lower bound surface is consistently this. That's nice. That's encouraging. It seems like things are looking good. But my upper bound, as I go up like that, well, for some points, the upper bound point will be on that face. But for other points, sort of further into the page, the upper bound will lie on that face. Not consistent. Not good. Everybody see the problem? So Oh, and you know what? Even even worse, for some points, like real close over here, for some points it would be on that one. This is a really bad choice, right? Highly inconsistent as to where your upper bound face is going to be. So that's a bad direction. Okay. All right. So, and now I'm going to let y'all think through the rest of these details. Again, the big idea was that we're projecting back into the XZ plane, slicing up that triangle gives you these bounds. The lower bound, I guess I'm doing it after all, the lower bound face is that plane where y is 0. The upper bound face is this, where there's an equation in which you can solve for y, and that gives you this, and there's your bounds. Okay, last example. We'll be quick with this one. This is a really weird shape. I just like to show off all the cool, fun stuff you can do with this projection idea. Notice first, let's try to get this all onto the page. Notice first, it leaps off the page at us that we want to put dy on the inside. Because I'm happy to solve for y as functions of x and z, but I really, really, really don't want to have to solve for x in terms of y and z. I can see the writing on the wall. That would be clearly bad. Right? So that strongly advises putting the dy on the inside, which puts x and z on the outside, which means I'm going to think in terms of projecting to the xz plane. And the xz plane projection's not that bad. There it is. Disk. Which I infer from the picture. Again, notice how you have to have a good picture to make that inference. Right? Really important to have that picture. Your lower bound surface is this one, which has this equation in which you can solve for y, and it gives you this. Your upper bound surface is that, which has that equation in which you can solve for y, and it gives you that. And we're done. Does everybody see the broad strokes there? Little details. You got to make sure you go through and check the details. Think through where I solved, where the intersection is and the outer bounds, etc. I want to make sure to think that through. This is the big broad strokes. Okay. All right. So, moving along. That does it for 5.4. We're going to move to 5.5. This is a big topic. This is another one of these giant sections. This is going to be at least 3 lectures, and of course we only have 15 minutes left for today. So my best guess is that 5.5 is going to take us the rest of today. Today's Tuesday? Probably the rest of this week. So again, our textbook makes these massive, gigantic monster sections, and then we'll also have these little narrow, teeny tiny, little itty bitty sections. I think that's funny. Okay, so what's the deal with change of variables? As I like to do, as I've done many times in the past, I think it's very valuable to start with a single variable calculus concept, because y'all know it already. You're already good at single variable calculus. And what I can do then is just take a certain very carefully selected point of view on that single variable calculus concept that I know you know, and then use that as a launching point to make an analogous approach in multivariable. So we did that with what's a derivative. We started with what's a single variable derivative and came up with some analogous ideas. Likewise, what's an integral? Well, we started with what is a single variable integral, and we used that to motivate multivariable integrals. Okay, so our single variable launching point here is going to be the substitution rule. which I know y'all have seen before. You might not have seen it written as an equation, but I hope this isn't a hard pitch. Looking up, forget about the diagram I have up here, just looking at this equation. The big idea is whichever direction you're going, you decide what expression from your integrand do you want to rename, for example, to be just x. And with that done, then you're going to need to know what is dx. Well, dx, a little bit of algebra, dx is g prime dt. Right? And then you kind of plug those in, and that means that these two integrals are equal. And you can use this again in either direction. You can view it as, well, I started with a dt integral, and I turned it into this different dx integral, or vice versa. You can think of it as I started with the dx integral, and then I plugged in the other direction, and got that dt integral. Either way. Right? Familiar? All right, so again, I want to take a very particular point of view on this. This is going to seem a little weird. This is going to seem sort of like hard to motivate, but this is what we need. This is the angle we need to take so that we can motivate a natural extension to multivariable. And here it is. We start with an integral. A dx integral, let's say. The dx integral has a domain. Like so. If you can find a way to view that domain as being the image of a different domain, then once you've written down this function, and keeping in mind that gives x as a function of t, right? X is g of t. Once you've written that down, then everything that you have in your dx integral, you can just kind of rewrite all those things in the dx integral. Just rewrite them all in terms of t just by plugging in, and that will then do what I call pulling back. That will turn our dx integral into a dt integral. And all of that comes straight out of what your g function is, right? So in particular, because I arranged my x domain to be the image of my t domain, let's see here, where's my, here we go, orange. So x, of course, is g of t. Plug that on in. Dx, as previously discussed, is g prime times dt. You plug that in, and the punchline is, well, we started with a dx integral. We've now converted that into a dt integral. Okay, so with details left out and just broad strokes, if you start with a dx integral, if you view the domain as an image, then you can pull back. Wrong color. You can do what I like to call, what is commonly called a pullback, namely the function goes left to right, but the expression goes right to left. The expression gets pulled backwards through the function. Right? Points go left to right, expressions go right to left. That's how plugging in works. Does that make sense? Now, a related important idea, and I think this is important, is do notice that dx and dt are not the same thing. Dx represents a little slice of the x-axis. Dt represents a little slice of the t-axis. They're not the same. Of course they're not the same. You can see this from a couple of different points of view. On the one hand, well, we've got this equation right there that says how dx and dt are related. Just the algebra alone shows they're different, right? But also, you don't even need the algebra. Think about what the function does. That g function's not necessarily simple, not necessarily linear. It's going to be some kind of weird function. It's going to stretch things out, right? So, for example, maybe this point goes to there. Does that automatically tell me where this point goes? No, it could go quite a bit further over. Because G is some wacky, weird function. Does that make sense? So we're going to be interested in by what factor does this little interval get stretched out, what I like to call stretched out. So in particular, we start, let's see, I was in highlighter mode. So we've got dt represents that little size, and then we've got dx is the, as I've drawn it here, bigger size, and the factor by which things get stretched out, you'll notice here, is G prime, and this is what I call a stretching factor. That's telling you how much bigger the output interval is than the input interval. How are we doing? Okay, so that's our point of view. And again, I know you know change of variables, and I know this seems like a weird point of view on change of variables. Right? Okay, so big points. The idea of a pullback, right? That the expression is going to go backwards through the function you set up, and the idea of a stretching factor, that this little piece gets stretched out by some amount to turn into this bigger piece of area over there, or piece of length over there. Okay, so with that in mind, here we're going to do a multivariable version, and we're going to get started anyway on a multivariable version of this. Let's see here. So there we go. Let's do it about like this. So suppose we have ourselves an integral in the xy plane, double integral, some domain, some wacky domain like that. By the way, I don't like that domain. Right? That's a weird domain. Look at all the corners. Imagine slicing that up. You're going to get corners. And whichever way you slice, you're 100% hitting corners. Probably two of them. Bad domain. Right? So if, big if, but if, and surprisingly often this will work, but if I can find a way to view that ugly domain that I hate, if I can view that as being an image of something nicer, if I can view that as being, here's the dream, if I can make it the image of a rectangle, wouldn't that be awesome? Because if I can make the right domain the image of some nicer domain on the left, then the pullback, we got to think through the details there, but the pullback won't any longer be an integral on this terrible domain over there, right? It will instead be an integral on this much nicer rectangular domain over here, and looking at this integral, can I compute this integral? I'm a lot less scared of the integral on the left because I'm not going to hit any corners as I slice it up. That makes sense? Yeah.
This is like U substitution, right?
It's that's right. So the analogy I'm making here is to substitution. People do like to call it U substitution. I've never understood why they feel the need to throw the letter U in there. It's non-critical. You can call it V if you like. But yeah, I know what you mean. Yeah, totally. So it's just, so this is the single variable substitution, and this is literally just a double integral version, a double integral analog of substitution. Absolutely. Yeah. All right. Details to follow, of course. Okay, so what do I do with this integral on the right? What do I do with the x and the y? Well, that's what G does. G literally gives me x and y explicitly as functions of my new variables u and v over there. So just write that down. X and y are literally functions of u and v. And then there's the nasty question, which is, what do I do about the stretching factor? What is, I'm going to have to clean up a mess here, what is the difference between how big that little piece of area is versus how big this little piece of area is? By what factor do I have to multiply the smaller, seemingly, as I've drawn it here, the smaller green area to get the larger blue area? How much does this stretch out the domain, in other words? And that is not immediately clear. Certainly not from this picture. So because we have a lot going on at this stage in the development, and I think it's good to kind of, let's try to get some wins in the win column. I'm going to momentarily just assert a formula. We'll talk later about where this comes from, but the stretching factor, the thing that you put in there to kind of make everything work, it's right here. There it is. It's the absolute value of the determinant of the derivative matrix. That's all it is. For the moment, you're just going to trust me on that, and we'll come back later and talk about why it's true. But absolute value of the determinant of the derivative matrix. You'll recall, of course, that the derivative matrix is just the matrix of partials. And I find it very convenient, and I hope you will too, I find it very convenient to rewrite, I'm going to be careful about this, the determinant of the not the matrix itself, the determinant of that matrix. Very nice to write that like this, and you can almost kind of see the motivations. After all, that matrix has partials of x and y, doesn't it? With respect to u and v, right? And isn't that kind of what we sort of, I mean, if you will, be flexible with the notation here. That's kind of what we've written down with this notation I have in blue here. And then just to also illustrate how handy and notationally convenient this is, recall that I can think of areas in the xy plane as dx dy. I can think of areas in the uv plane as du dv. And if my stretching factor, if I write that stretching factor like this as partial xy, partial uv, don't forget your absolute values, it's almost like that cancels with that. They don't. It's not. That's an absolute crime, right? Please don't tell my old math professor that I said that, right? It's complete nonsense. Absolute 100% nonsense. But it looks good on the page. It's wonderful as a memory tool. We're going to find in some cases that it's hard to remember, wait a minute, which way was I going? This keeps track for you of which way it goes. So I'm a big fan. Encourage you to use this notation, but I got to emphasize, it's absolutely not a fraction. It's a determinant. It says so right there. Not a fraction. It's written as a fraction. It behaves almost, kind of, sort of like a fraction. But it's not, and that's not a cancellation. Okay, so this is a pretty good place to draw the line. We'll draw the line right here. We'll pick up here on, tomorrow, whatever that is. Wednesday? Yeah. See y'all later. Have a good one.